So here, this is the fourth question. So they're asking to show that identity operator is having all the diagonal elements 1 and the rest of the elements are 0. Okay, so first let us take example and after that we will do that mathematics. So here I'm taking basis states, three basis states I am taking. So V1, V2 and V3 are the three basis states. Now if you take identity operator operates on V1, we'll get V1. So this can be written as 1V1 plus 0V2 plus 0V3. And similarly, if I identity operator operates on V2, we'll get V2 only, same state. This can be written as 0V1 plus 1V2 and plus 0V3. If you take that V3 similarly, this identity operator operates on V3, we'll get V3 only. And this can be written as 0V1 plus 0V2 plus 1 into V3. So if you write this in the matrix representation, so this is the identity operator, and here we have input basis V1, V2 and V3, and here we have output basis V1, V2 and V3. So here input and output basis both are same. Now see, if I operates on V1, we got a linear combination of this V1, V2, V3. So here is a 1 V1, this is a V1, that's why it's 1, and a 0 V2, and this is also 0. And here the same, a 0, this is a 1 V2, here 1, and this is 0. So 0, 0, and here it is 1. So we can show this by using one example like this. Let us do some mathematics. So by using completeness rule. Okay, so here I'm going to use this completeness rule. So here I'm taking the input basis Vi. So under this transformation identity, that means identity operator is operating on this. So I think we can write this as I Vi. So now I'm using this completeness rule and replacing this identity operator like this. Summation over j. This is the outer product Vj like this. Now just take it and substitute. Now summation over j, this is a Vj outer product into Vi. Now this is nothing but identity operator operates on Vi. So if you carefully observe, this is nothing but the inner product, so which is a scalar. So here we have written, we can write summation over j, the inner product Vj, Vi, and this is a ket Vj. And this inner product is nothing but a Kronecker delta function, which is a delta ij. So now this is the summation over j, delta ij, ket Vj. So what is the meaning of this? So whenever identity operator operates on this Vi, we got this. So Kronecker delta. So this value equal to 1 if I is equal to j and 0 if I is not equal to j. What is the meaning of I equal to j? Diagonal elements. So here this I equal to j is nothing but diagonal elements. And this I is not equal to j means of diagonal elements. So all diagonal elements are equal to 1 and all of diagonal elements are equal to 0. Like this we can do by using this completeness rule. So here this is the next question. So they are asking uh, verify this is an inner product. So here what is this notation? So actually let me introduce first Dirac notations. Okay, so here I'm introducing this Dirac notations. After that we will discuss this problem. So whenever You have a state vector in the Hilbert space. This is represented by ket psi, and the corresponding complex conjugate, that is a psi star, is represented by a bra vector. State vector is represented by ket vector, and its corresponding complex conjugate is represented by bra vector. Now, whenever there is a constant in ket vector, that constant will be out as it is, okay, and whenever a constant in a bra vector, so you will get a complex conjugate of that A into bra vector. Constant you can write anywhere, here or here, does not matter. Whenever an operator is there inside the ket vector, so this will be out as it is, and whenever an operator is there in the bra vector, so here you must be very careful. So you can't write this operator A out this in this here. So you have to write like this. This is the psi. Whenever an operator in the bra vector, you will get the Hermitian conjugate or complex conjugate, that is A dagger. But you should not write here. You have to write beside this vertical line only. So these are the these are basic Dirac notations. Now let's come back. So what is this notation? So here in the textbook, they are using this notation. So what is the meaning of this? So here one state vector, here one state vector, that is a psi comma phi. So this indicates the inner product. So in a Dirac notation, we can write this as a bra and a ket, bra psi and ket phi. So now this inner product is having a few things to verify. That is, this is a linear in the second argument and conjugate linear in the first argument. So, and the next one is a norm is always positive. So these are the three conditions we have to verify. So once again, first one is linear in the second argument. And the second one, here we have to show this a complex conjugate. For example, we have phi psi, its a complex conjugate is nothing but psi phi. And the third one, the norm is always greater than or equal to 0. And another one is conjugate linear in the first argument. That is the next question actually. So we will discuss here. Right. Okay. So let us prove these things. Now, first one, this inner product is linear in the second argument. Second argument. What is the meaning of this? So this means, now for example, I'm taking this psi comma phi inner product. I'm talking about this second argument. So this is nothing but psi as it is. And the second one I'm writing as a linear combination, a summation over I, lambda I, phi I. And I have already given this notation. Whenever there is a constant in the ket vector, it will be out as it is. Summation over I, lambda I, this is psi phi I. Okay, so which can be written as in this format. So this is nothing but lambda 1 psi phi 1 plus lambda 2 psi phi 2 and so on. So this is the mean linear in the second argument. Okay, and the second one. So here, if you take the complex conjugate, these are two states are interchanged. Let us see this one. Now here, I'm taking first a phi comma psi inner product. According to this Dirac notation, I can write this as phi and psi. Now for this, I'm taking complex conjugate. I'm taking this complex conjugate, that is phi comma psi, the complex conjugate, which is nothing but phi psi complex conjugate. Here I have already defined ket vector complex conjugate. That means in the Dirac notation, if you take a ket and apply conjugate, you will get a bra and vice versa. So once you apply the complex conjugate, this bra vector will become ket vector and this ket vector will become bra vector. So this is a psi and phi. So which we can write this as psi comma phi with this notation. So second one is also proved. And third one, so this is the norm. Norm is nothing but length of the vector in higher dimension. So let us take this psi comma psi, which is nothing but bra psi and ket psi. So this is the bra vector and ket vector. We can write this as psi star into psi. So use this notation, which is nothing but mod psi square. Whether psi may be real or complex, but once you take the mod square, this is always positive. This is always positive. So here we have discussed the three properties of this inner product, and the next one we will discuss this as another property. So here they are asking, show that inner product is a conjugate linear in the first argument. Okay, so let us take this inner product. So here I am taking a psi comma phi. So I'm using the Dirac notation for this. Okay, so this is the psi and phi. I'm talking about this first argument here. So this is summation over I lambda I psi I, which is a linear combination of basis states, and this is a phi. Okay, so we have already discussed earlier, if any constant is there in the bra vector, you will get its corresponding complex conjugate. So here, so this is nothing but the summation over I. This lambda I is in the bra vector, so lambda I star, this bra psi I phi. So this is nothing but lambda 1 psi 1 phi plus lambda 2 lambda 2 star, lambda 1 star phi plus so on. So if you want to write this notation given in the textbook, psi comma phi equal to lambda 1 star psi 1 comma phi plus lambda 2 star psi 2 comma phi plus lambda 3 star psi 3 comma phi plus so on, like this. So finally, inner product properties, it is a linear in the second argument and a conjugate linear in the first argument, and whose whose norm is always positive, and it satisfies this complex conjugate rule. Right. So here this is the next question, and this question is related to orthonormalizer condition. First, let us discuss what is this orthonormalizer condition. Orthonormalized condition. Right. So for example, we have two state vectors. Let us say psi I, psi j. This is nothing but delta ij, which is a Kronecker delta function. So this value equal to 1 if I is equal to j, and 0 if I is not equal to j. So that means this one condition is called normalized. That means these two are same, and if it is equal to 1, that state is said to be normalized state, and a 0, this is a orthogonal condition. So this is the orthogonal condition and this is the normalizer condition. Okay, so first let us check whether these are orthogonal or not. Here they have given, so W equal to 1 1. I'm writing the ket vector notation. See, ket vector you have to write it as a column matrix, and the bra vector you have to write it as a row matrix, but you have to take complex conjugates of the elements. I repeat, ket vector column matrix as it is, but bra vector you have to take a complex conjugate and write it as a row matrix. But of course here we have all real elements only. V equal to this is a 1 minus 1. So let me check whether this these two are orthogonal or not. Now I'm taking the inner product of W and V. These two states are different. So if I get 0, those are orthogonal. Let us check. So this is the bra vector. So I have to write it as a row matrix and no complex conjugate because these are real. And here this is the ket vector, which is a column matrix. So if I multiply here, I will get 0. So this is, I mean, these two states are orthogonal. And after that, they are asking what is a normalized form of these two states. They are not normalized because if you take the dot product here, you won't get it 1. That means, sorry, inner product. Inner product of W, if you take, you won't get 1. So how to get this normalization? For example, you have a state psi, which is AB, and its normalization constant is given by, the normalization constant is 1 over under root mod A square plus mod B square. We don't know whether A and B are real or imaginary, so that's why we better to write this general form. So by using this, I can take a W, which is 1 minus 1. Its a normalization constant is 1 over under root 1 square plus 1 square. This is a 2. So the normalized form is 1 over root 2, 1 minus 1. And here W similarly, which is, okay, I'm sorry. So this is a plus 1 and this is 1 minus 1. Okay, so normalization constant is again 1 over root 2 and this is 1 over root 2, 1 minus 1. That's it. Okay, right. So if you have a doubt, so please contact. Okay.